Picture two impossible objects hurtling toward each other in the dark. One eats everything nearby, forever. The other refuses to let anything in, ever. Comment sections have a name for the result. A grey hole. A joke, upvoted thousands of times. But physicists have spent 50 years working out that the joke doesn't hold up. And the real answer is far stranger than a colour caught between black and white. Start with the black hole, because we've actually seen one. In 2019, the Event Horizon Telescope captured Sagittarius A star and M87 star, rings of superheated gas bent by gravity so strong that space-time itself flows inward, faster the closer you get. At the event horizon, that flow hits the speed of light. Nothing outruns it. Not light, not you. Cross that line and there's no crossing back. A white hole is the mirror image, at least on paper. Same singularity, same mass, same gravity, but space-time flows outward instead of in. Try to enter, and the outward flow pushes back at exactly the speed of light. You never get in. Nothing ever has. No telescope has photographed one, because as far as anyone can prove, none exist to photograph. Neither object was dreamed up first and tested later. Both fall straight out of Einstein's field equations. Solve them for a collapsing star and you get the familiar black hole. But the equations are time symmetric. Run the same math backward and a second, equally valid solution appears, a white hole. Carl Schwarzschild found the geometry in 1916. Decades later, Martin Kruskal's coordinates showed both solutions living inside the same mathematical object, stitched together at a single point. A white hole isn't a fringe idea bolted onto black holes. It's the other half of the same equation. So what happens when you put them together? The obvious guess, the one nearly every video reaches for, is that the bigger one wins. Black hole swallows white hole, or the reverse if the white hole has more mass. Equal mass, and it's shrugged off as a coin flip. Case closed, or so it seems. Except that framing skips a question nobody bothers to ask. Does a white hole even survive long enough to have that fight? In June 1974, physicist Douglas Erdley worked out that it probably doesn't. A white hole's outward flowing horizon is exquisitely fragile. Drop a single speck of matter near it and that speck can't fall in, but it also can't outrun the horizon fast enough to avoid meeting it. That meeting does something drastic. It converts the entire outgoing horizon into an ordinary, inward-flowing black hole horizon, almost instantly. One stray photon is enough. Physicist Carlo Rovelli later joked that white holes got killed twice that same month, once by Erdley's classical instability, again by a separate quantum argument about particle creation near the horizon. The takeaway is blunt. A macroscopic white hole meeting real matter, real radiation, even the faint background hum of the universe, doesn't stay a white hole for long. It isn't patiently waiting for a black hole to arrive. It's a hair trigger that fires the instant anything touches it. There's a second, older problem too. White holes violate the second law of thermodynamics. Entropy should never spontaneously decrease, yet a white hole's horizon behaves as though it does, spitting out order instead of swallowing disorder. General relativity doesn't forbid the solution, but it was never built to enforce thermodynamics in the first place. Not proof of impossibility, a warning light that the math might be legal without being physically real. Put those two problems together and the mass ratio question, who wins when they're evenly matched, starts to look like the wrong question. Long before two such objects would touch, the white hole's own fragility would likely have already turned it into a black hole. The dramatic collision most videos promise probably never happens the way it's staged. Two black holes merge instead. No fireworks, no grey hole, just an ordinary, well-understood merger. But here's where it gets genuinely strange. Some physicists don't think white holes are separate objects at all. Carlo Rovelli and Hal Haggard propose that a black hole and a white hole are the same object, viewed at two moments in one continuous history. Matter falls in, gets compressed toward Planck density, roughly 10 to the 96 kilograms per cubic meter, and quantum gravity stops the collapse cold before a singularity forms. The object bounces. What emerges, reversed in time, behaves exactly like a white hole. They call the maximally compressed moment a Planck star. From outside, the transition looks nothing like an explosion. Time dilation near the horizon is so extreme that a bounce, lasting moments for the falling matter, could take billions of years to become visible. Haggard and Ravelli call the eventual release black hole fireworks, and suggest some of today's unexplained high-energy cosmic ray bursts might, in principle, be evidence of exactly this. It also reframes a question that shows up constantly in the comments. Is the inside of a white hole a doorway to another universe? In the classical Kruskal picture, the geometry connects to a region entirely cut off from ours, sometimes nicknamed an antiverse. But the Planck star model doesn't need a second universe. The matter that bounces out is the same matter that fell in, arriving back here billions of years later and unrecognisably transformed. No portal, just one object taking an extraordinarily long way home. If that picture holds, the question, what happens when they collide, is built on a false premise. There's no collision to referee. There's one object, one history, folded through a bounce so extreme it looks like two different things depending on which side you're standing on. The black hole matter falls into and the white hole something might one day emerge from aren't rivals. They're the same event, told twice, separated by more time than anyone watching from outside could sit through. None of this is settled. No white hole has ever been observed colliding or otherwise. Steven Weinberg's classic 1972 textbook on gravitation dismissed the idea outright, and most physicists still treat it as a mathematical curiosity, not a prediction about real astrophysics. What's changed is the toolkit. Gravitational wave detectors are now sensitive enough to hunt for the faint echoes a Planck star bounce might leave rippling through space-time. So next time that comment shows up, grey hole, case closed, the honest answer is stranger. Maybe nothing ever collided. Maybe it was one hole learning how to become the other.